All right, so let's keep going. Let's talk about PA4.
Yeah, that was the list.
He goes to the library the night back.
I don't know, I just not have to.
Uh-oh, crinkly. Yeah, we are.
That was Spencer.
Spencer runs with one of them.
Yeah. From Vancouver, Washington. I had to look at my notes from last quarter to see how it
All right, so programming assignment 4. This is your binary tree assignment.
Yeah, I didn't.
And this can be really cool once you start making some headway on it, okay? Because it pulls in a lot of things, linked lists and queues and everything we're talking about and we'll talk about next week with trees. So they all kind of come together. So you're building binary search trees, okay? Standard search order, larger things are on the right, smaller things are on the left, okay? And you're going to define an interface in your main program that lets the user basically add things to the tree, remove things from the tree, look at the tree, and so on. So just like we've been doing with lists and stacks and queues, kind of a test bed for your code. So the main program has a pretty simple command interface. You can say search space number, and it'll tell you if that number is in the tree or not. You can say d space number, and it will delete that number from the tree. If the number is not in the tree, tell the user it's not in the tree, I can't delete it. X will print out the contents of the tree, but it prints a whole bunch of information about the tree. So first, it prints the pre-order, in-order, and post-order traversals. Okay, so you traverse it 3 times. And each time that you print it out, I want you to print out a mnemonic, either NLR for pre-order, LNR for in, and LRN for post, followed by a colon, followed by one line of output of all the numbers in your tree separated by spaces, followed by a new line. So you get NLR, colon, and the pre-order traversal, and then LNR and the in-order, and so on. So you get 3 of these depth-first traversals, and then you print out a breadth-first traversal. So you print the string BFS, breadth-first search, colon, and then a list of the nodes in the tree, comma-separated, not space-separated. Then a list of the nodes in the breadth-first traversal. So we'll go through the BFS algorithm again next week, but it's going to use a queue. So keep your queue code from PA3. Don't delete it after you turn it in. And then tell me what the height of the tree is. So remember, an empty tree, if the root is null, has a height of -1. A tree with just a root has a height of 0. And there's a recursive definition for height. It's 1 plus the maximum height of the left and right subtrees. So put together a height function and call it and print out what the height is. So height, colon, followed by the height. And then check whether the tree is balanced. So we had a recursive definition of balanced. So decide whether it's balanced, print the word balanced, followed by yes or no. Okay, question mark gives you a help message, uppercase Q quits. If you type a number, it inserts it into the tree. And before you insert, make sure it's not already in the tree. If it is, you can call the user a moron and refuse to insert that number. But keep running, okay? And don't delete my files. All right, and anything else prints an error message. All right, details. Do not balance the tree. I don't imagine many people are going to want to write a tree balancing algorithm, but don't, okay? Don't do that in here. Because the only way I can assess this easily, aside from going through your code, which I will do, is to insert data in a certain order and then look at your different traversals. Okay, that's sort of my first read as to whether your code's doing the right thing or not. And if you balance the tree, that will mess it up. Okay, so don't do any tree balancing. Do your insertion just by moving down to the right leaf and then tacking on to the left or right child. And do your deletion by removing the largest node from the left subtree of the tree rooted at the node you want to delete. So move down to the node you're trying to delete, look at the largest node in the left subtree, move that up to the root. Okay? If there is no left subtree, then just change the root to the thing that the root is pointing to, which will be its right immediate child. So we've done this in class. We'll go through all of this again next week, but like I said, we don't have class Monday. So if you want to start making some headway, do the pieces that you can. Delete's going to be the trickiest piece. Breadth first search will be the second trickiest probably. And the others should be fairly straightforward if you understand the algorithms. All right, you want to make sure you free all your memory. So you're going to have all the memory for your nodes. When you delete a node, you want to free the memory. When you're done, you want to free all the memory associated with the tree. Just like the list, you can do whatever your favorite traversal is. And each time you visit a node, free that block of memory. And do it in a way that doesn't trip yourself up. And when you're done, all the memory should be gone. You're also going to have a queue. I suggest implementing your queue with a linked list because you've already got that code. If that's the case, you want to free all the queue's memory when you're done also. All right, yeah, use your queue from PA3. So do it as a linked list. Okay, use recursion. The things that we've described as being recursive: insert, search, delete, height, balance check, and all the depth first traversals. Do all those recursively. Breadth first will be implemented using a queue. So it's a loop instead of a recursive algorithm. It just doesn't work very well with recursion because recursion is fundamentally stack oriented and breadth first is fundamentally queue oriented. Take all your code, make a make file that builds an executable image called PA4. Put your source files and make file into a tar, upload it to Canvas. All right, so let me show you what this can look like. Yeah, I thought that would happen. All right, so nice little welcome message there. And let's build a tree of some data. So I'm going to insert a 20, and then a 10, and then a 30. Okay, 20 is my first number. That's going to be the root. 10 is going to come off here to the left. 30 is bigger than 20, so it's going to go to the right and get added right there. So let's just start building a tree with those values. So I'll do 20. I don't know what that means. I guess that's my prompt. I'll do a 10, and I'll do a 30. All right, so I should be able to search for any of those. 10 is found, 11 is not found. Should find the root, should find the right child. So X is the real fun command. So X shows you a bunch of different output. So the preorder traversal is 20, 10, and 30. All right, so preorder says visit a node and then visit the left and then visit the right. So visit the node, the root of the tree, that's 20, and then traverse the left subtree, which will just be a 10, and then traverse the right subtree, which will just be a 30. So that's a good NLR traversal. Left node right traverses the left subtree first, then visits the root, then traverses the right subtree. So 10, 20, 30 is good for left node right. That should always be in order. That's why it's called the in-order traversal. So whatever data you put into your tree, LNR should always be in increasing order. Okay, that's a good quick check. And then left-right node says traverse the left subtree, then the right subtree, and then the root. So 10, 30, 20, that's a good traversal order for left-right node. Breadth first search, remember we just go down one level at a time from left to right. So the first thing we're going to print is 20, and then we're going to print the 10 and the 30. So 20, 10, 30, that's good for breadth first search. And then the height of the tree, so an empty tree is height minus 1. So the depth of a node is the number of hops from the root to that node. So this node has a depth of 1. This node has a depth of 1. This node has a depth of 0. Maximum depth is 1, that's the height of the tree. So height is 1, and it is balanced. So that output all looks good. Let's go ahead and add some more data. So let's add a 40, a 50, a 45, and a 35. So this will be 40, this will be 50, this will be 45, and this will be 35. So that should be what my tree ends up looking like. So 40, I don't know what that's going to do, 50, 45, and 35. All right, so let's look at the traversal orders. So the in order, 10, 20, 30, 35, 40, 45, 50, that looks good. Breadth first search is an easy way to tell if you're doing the right thing because it's pretty easy to traverse this breadth first. The first thing we should get is a 20, and then we should get a 10 and a 30. And then we go down to a depth of 3, and we should pick up the 40. And then we go down another level, and we should pick up the 35 and the 50. And then we go down to the last level, we should get a 45. I'll be really embarrassed if that's not what we got. 20, 10, 30, 40, 35, 50, and 45. And it's definitely not balanced anymore. And this is our deepest node, and it takes a total of 1, 2, 3, 4 hops to get to the root. So the height of the tree is 4. All right, that's the behavior of the program. Okay, deletion. So let's just delete the root of the entire tree. So when we delete this, we're going to take the largest node from the left, which is a 10, and put that up here. Big X. All right, the height is still 4. And if we delete the 10, there's nothing on the left subtree. So it should just change the root to be the 30. So if we delete the 10, then we look at the data, you can see in the breadth first, the first node that came out was 30. That's the new root. But you're going to make yourself lots of pictures of trees. You're going to put in nodes in different orders, and you're going to look at what you're outputting and make sure that it's making sense. Okay? Delete's going to be the trickiest part because it's got all these different cases. But you should be able to delete any node in this tree. So try deleting the root of the entire tree first, and try it when you have lots of stuff on the left and lots of stuff on the right. And then try deleting something that's not at the root. And those are good edge cases. Try deleting a leaf node and so on.
Why did 10 go to the top instead of 30?
So our delete algorithm to delete a root is always take the largest number from the left subtree and make that the root. So take the largest node, which is a 10, that becomes the root, which means it adopts on the right whatever the root's right child was. So 10 is the new root. And remember, we're not just copying data values. Okay, when we say replace the root with the largest value on the left, we're not just changing this to a 10. Okay, because this may have a bunch of things hanging off of it, and we want all of those to get dragged up to the root also. So we're actually making this the root, which means adopt whatever the old root's right child was. All details we'll go through more carefully next week. So let's just make a nice balanced tree. So how do I get out of here? Oh, so Control D to exit. So I don't have an exit command on this, so Control D will exit. How do you pick up Control D? fgets will return null if you enter Control D in the beginning of a line. And that's nice because it lets you drive this from a file for standard in. You can do input redirection, for example. So let's make a tree. 10, 5, 20, 2, 7, 15, 30. So 10, 5, where the heck did 50 come from? I don't know what I'm doing. 10, 5, 20, 2, 7, 15, and 30. All right, so my breadth first search looks correct. 10 followed by 5 and a 20, followed by 2, 7, 15, 30. The height of the tree should be 2, and it is balanced. Okay, it's very nicely balanced. So what happens if I delete the 20? 15 should adopt 30 and be the new right child of 10. So the 15 basically comes up here. So if I delete 20, and then I do my traversal, my first node is a 10, my second level has a 5 followed by a 15. Right, we're looking right down here. And then the lower level has a 2, a 7, and a 30. So that's promising. That doesn't tell you that it's absolutely correct. But if it doesn't segfault and if the BFS looks good, you're probably on the right track.
So the balance has nothing to do with the, like if you had put that data in a different order, it would then not be balanced?
Very possibly, yeah. So, for example, right, so this tree has a height of 6. It's definitely not balanced. It's this big lopsided tree. Yeah, to balance it, what we would actually do was when we added the 3, we would say this side is more than 1 off from that side. We do a rotation like this, and we turn it into this.
Are we not going to be doing that this term?
I think we're going to do that in 223, because that'll be fun.
I guess it's easier with Java though, right?
Oh. It's easier in the sense that you don't have all these mallocs and these stars and things like that, right? Java really works with, we're working with objects here, but we don't really have objects in C. So we cobble them together kind of with our bare hands by using mallocs and stars and dereferencing pointers. And Java, it's part of the language. So the code certainly comes out cleaner, and it's a lot more comfortable usually to read and write and work with than C, but the basic algorithm is going to be interesting regardless. All right, so that's typical behavior. So I can delete most of my nodes, and all I've got left is a single node 7. And if I delete that, now my tree is empty, so my traversals bring up empty strings. I should have had a new line after my BFS. My height's -1 and it's balanced. And if I try to delete from there, nothing's in the tree. All right, so suggestions. All right, suggestions. So the first 2 algorithms I would recommend writing are insert and the in-order traversal. Okay, initialization is just setting the root equal to null. So you don't even need a separate routine for that, but you can make one if you want. Root equals a nit, and a nit just returns null. But the first pieces of code are going to be inserting into the tree and doing the in-order traversal. Okay, insert is recursive. If your root is null, make a node, store your data in it, set the leaf children to be null, and return its address. Otherwise, if your data is smaller than the root, set the left child equal to insert of the left child, comma, your data value. So call insert to add to the left subtree, and then make root point to that on its left. If your data value is bigger than the root value, call insert on the right subtree to put your number into that, and then have root's right child point to that tree. So insert, if you set it up right, insert is a few if statements and 1 malloc. Okay, but getting that set up just right is the fun part.
And a bunch of papers.
Yeah, yeah. Once that works, right, then you're off and running, because if you can do recursive insert, the other stuff is just more of the same. Okay, so that's a good one to start with. And traverse is even easier to write, but not really very useful until you have trees. But traverse is just, if the tree is empty, return. Otherwise, traverse the left subtree, print the root, traverse the right subtree. So it's really like 2 or 3 lines of code. So you can write traverse, and you can build a tree by hand like you've done in your ODPs and pass it to traverse, but get your insert working sooner rather than later, and then you can have fun with that. Just keep inserting things, doing the in-order traversal, and you've got something that's sorting your data for you automatically from there. So that's nice. All right, after that, deletion is your next major hurdle, but you don't have to do deletion next, right? You can do search, but search is exactly the same as traversal, right? If the root's null, then your number is not found in the tree. If the root data equals your number, it is found. Otherwise, search the left and right subtrees, and if it's found in one of those, it's found in the tree. If not, then it's not in the tree. And like I say, once you've got a recursive insert, these others are just variations on a theme. So search is pretty straightforward. The other traversal orders, preorder, postorder, is really just rearranging these 3 statements in your traverse code. And then breadth first search is a whole different ball of wax. But we'll talk about that in a bit. And then deletion is sort of the real challenge there. The biggest challenge, let's put it that way. It's all challenging until you get it to work. Deletion is a whole separate assignment, basically, but it's not. It's part of this. But I would get everything working except deletion, right? And save your code so you don't go crazy making changes to things that work, and then start working on deletion. And delete from the root first, and then work on deleting things in subtrees. All right, questions on that?
I know we're not going to go into it right now, but is breadth first search like heavily recursive?
It's not actually. It's really an iterative loop. Sorry, say again?
Is that the thing you were saying is queue-based?
Yeah, that's queue-based, and recursion kind of works well with stack-based things. Well, let's talk about, since we got a few minutes, let's talk about breadth first search. Because it's actually a fun way to use your queue code once you turn it in for PA3. We're not going to use all of those. I just like writing trees. All right, so there's a tree. We want to do a breadth first traversal of it. So the algorithm is pretty straightforward. So add, let's say insert the root data. Just insert the root. So you probably want a queue of struct nodes, right? Instead of just a queue of integers, you want a queue of actual struct nodes. So your queue is going to be a linked list where the data part is a struct node, and then the next part is a pointer to a struct q node, right? So this is a struct t node, but we'll just call it root for now. So insert the root into your queue, and now we begin a loop. So while not queue empty, so while there's stuff in the queue, remove one node from the head, print its data, and then add its children. So if node left is not null, insert node left. And if node right is not null, insert node right. And that's your whole loop. So you seed the whole process by inserting the root. And then you just iterate as long as there's stuff in the queue. Remove what's at the head of the queue, print its data, and then if it's got a left child, add that to the queue. If it's got a right child, add that to the queue. And go back and just keep doing this. So what does this do? We're going to start off, we're going to insert the root of this tree, which is an A. So here's our output. So we're going to say while the queue is not empty. While the queue is not empty, it's got something inside it. So set node equal to the head of the queue. So remove the A and set node equal to that. Print out node's data. So I'm assuming that's the character A. And then if node left is not null, insert node left. Well, node left is B, so let's insert that to the queue. And node right is C, so insert that to the queue. Go back to the top of the loop. So queue is not empty. Remove the head of the node, the head of the queue, which is B, set node equal to that. Print its data. Take its left child, add that to the queue. Take its right child, which is E, add that to the queue. And just keep going. And you can start to see what's going to happen here. We're going to deal with C before we deal with these things we just pushed in. Right? We added a C to the queue because it was a child of A. We're going to pull that out of the queue before we put any of C's children, before we deal with any of those. So we're moving slowly down to deeper levels of the tree. So back to the top, remove the C, set node equal to that, print its data value, take its left child, add that to the queue, take its right child, add that. Go back to the top, remove the D, set node equal to that, print its data value, push its children into the queue. So it's only got a left child, which is H. There's no right child, so we don't insert anything there. Remove the E, set node equal to that, print its data. E has a left child, I, it has no right child. And we just keep going. All right, we'll remove the F, print its value. There's nothing on the left, there's a right child. Remove the G, print its value. G has no left child or right child, so we don't add anything to the queue. Remove the H, print its value. Where is H? H has no left child and no right child, so nothing gets added. Our queue is almost empty now. We remove the I. That's our node. Print its data value. Take its left child, add to the queue. Take its right child, add. Remove the J. Print its data value. Left child is M. Right child is null. We don't add it to the queue. Remove again. There's a K. Print its data value. K has no left or right child, nothing gets added. Remove the L, print its data value. L has no left or right child, nothing gets added. Remove the M, print its data value. M has no left or right child, nothing gets added. We come back to the top of the loop that says, well, queue is not empty. Well, now the queue is empty. We exit, we're done, and there's your breadth first traversal. So the algorithm is not that complex, but the implementation is filled with all kinds of nuances, right? Starting with the idea that this is a queue of T nodes, right? Tree nodes, as opposed to just a queue of integers. So your queue is a linked list, A linked list has two pieces, a data piece and a next piece. The data piece, instead of being an int, is going to be a struct tnode. Okay, or you could make it a struct tnode star and store the address of these things. That's going to work better. So now your queue structure will look a little weird, but only if you think about it. So struct queue node. This will have a struct tnode pointer, which is data, a struct queue node pointer, which is next, and a struct queue node pointer, which is tail pointer. And if you think about it too much, it's confusing, but if you don't think about it, it works. Don't think about it. And this makes fun pictures if you actually try to draw it out. Because now what's in your linked list, which is your queue, is actually a whole tree, right? It's actually the address of the root of a tree. But you can think of it as a big list with little trees inside each node, right? And that's kind of cool. All right, other questions? So let's leave it there for today and for the week. I have office hours from 2 to 3, and tomorrow's office hours only go until 12:30 instead of 1, so I changed that last week, but didn't mention it. Yeah, so today would be a better time to ask questions on PA3.